Good afternoon, everyone. So myself, Shashidhar. Actually, I am the head of R&D in Delta India Electronics, and today I'll be presenting on sustainable transportation as a general topic. I will not go more details into uh, uh, the uh, the depth of the power electronics what we do, but it is more of the engineering talk what I will be doing. But however, the details can be discussed because I cannot cover everything in 45 minutes. So before I get into the topic, I wish to go through little bit 2 slides on my organization, and then quickly I move on to. So this company started in 71. So and our company is purely focuses on power electronics. So today we make a revenue of 12.73 billion, and so we have committed ourselves for the RE100. I think we are going to achieve much before 2030, most probably maybe 27, 28. Our company is able to do such a fantastic performance in last 50 years by keeping the focus on the technology, customer centric, and then the focusing on the environment or caring for the environment. Globally, we are 84,000 people, so this year expected to be 90,000 people, and we have 9,000 R&D engineers globally, and we have R&D centers at 75 locations. And all locations focus, 90% we focus on power electronics. This is about India. So in India, we have come up with our own R&D center, which is spread across 7 acres, and then we have a place for 2,000 engineers. But right now we are only 300 people. So I have a lot of work to fill up 1,700 people in the next 5 years. So we have 2% PhDs, 30% masters, and then rest mostly bachelors. We work in a very wide spectrum of power electronics. We work on products in India as small voltage as 48 volts and 100 VA to all the way up to 7.5 MVA systems with 52 kilovolt. So I have people who works with, with their hands, and then they play with that, and some people sit far away with the power electronics and work. So we have the state of the art lab, especially with this insulation class, 52 kilovolt class. And so this is about our the investment in the next years. By 28 we are expected to have close to 1,000 people, and then in 33 it is going to be 1,500, focusing only on power electronics. So we are also starting our the software division, which is required, because today power electronics is, without the software, power electronics has no value. So our separate investment, which is also going on the software side, which is specific to our own product support, backend as well as on the system, what we call on the client as well as on the server side, what we say. So client means for example, EV charger is my client. So client has to be connected back into the server. So both the sides I need software engineers. So we are investing, that's our next phase. But this what we show here is purely power electronics engineers. Could be firmware, electrical, mechanical engineers. So let's get on to the topic what I supposed to talk, which the Kaushik has assigned me. And so before really get into the trend in the automotive, what is happening, so let's see the history. The first four-wheel which actually came into existence, we can actually date back this to 1777 when we had the steam engine based four-wheeler. But actually real commercialization of four-wheeler started only in the late 1900s with the IC engines in the 19th century, end of 19th century. That was with the 1884, this, the Daimler launched this. So Mercedes, which is today's company, which launched this, but it was commercialized. But actually very important, what we should not just forget here. So for the success of the automotive only started when actually the Ford introduced mass production for this. So without that, we would have not achieved what we achieved today. It's because he wanted to, because here all skilled labor used to make these cars. Daimler had, trained, intelligent fellows, made them highly skilled, and then they used to manufacture this. But actually, Ford wanted to take the dumb fellows, train them, put them on the process, and then they make actually more vehicles at a very cheaper cost. So that is where actually revolutionized the automotive, the trend later changed. So let's look into the green vehicles. When did they start? So 1881 was the first vehicle, actually a demo vehicle, which was, I think this was in France, which was actually ran with today's what we call VRLA batteries. And yeah, commercialization happened in 88. It happened even in two places in Europe. One was in UK as well as in Germany. But actually mass production, if you see from 1888 to the real mass produced EV, took very, very long time. There are a couple of reasons for that, we all know. Because the technology was not matured, commercialization was very difficult, and nobody wanted to mass produce. It is not even the Tesla is considered as a mass produced vehicle, because its first vehicle was actually the Nissan Leaf, because they produced first vehicle which is more than 500,000 on the market. So what do we take away from this slide is basically some actually evolution. You see, for example, the evolution happened very fast here when actually the four-wheeler, if the Ford would have not been there, it would have taken maybe another 30-40 years. So, but whereas here, you see, there it was not actually about the technology, it is more about, how do you manufacture this. So here we did not have that problem, here we had the problem of technology. So one or the other problem actually caused electric vehicle to really commercialize as mass produced has actually taken us a long time. So now we all accept that the electric vehicles are going to be there on this market. They are going to throw away the existing technology. And before we go and dig more deeper, so I wish to show one more slide about how this disruption could happen. How the disruption can actually change the scenario, especially in automotive. So before automotive, I want to just give you an idea how this technology can actually, sometimes it disrupt and sometimes it sustain. For example, everybody thought when that ATM came in, so they gave all the features, all the banking things you could do with the ATM machines. But actually that did not replace all the banks. Though it actually came with a philosophy that it will replace banks, we will not have any banks. But actually they did not happen. But where the same thing, if you see when MP3 players were launched, actually they basically killed the CD market. So what we call this as actually disruptive, this we call it as sustainable technology. So similar disruption, one good example to understand is about the automotive when it happened. See, this is in 1900, Easter morning, as you see, all are actually cars. You can actually only locate one car there, one IC engine car. But actually in 1903, only in 3 years, on the same Easter morning, so you have only one car there. This is how actually the scenario changed in actually automotive segment. Why I am showing this is, India, the government of India is pushing very hard on making 30% vehicles, electric vehicles by 2030. Hypothetically, we assume they implement this or they are successful implementing this. What is it going to happen? Let's say I am taking an exponential curve, because this is today, currently we sell hardly around less than 1% or maybe 1% of the vehicles are actually electric vehicles what we sell. Approximately 80,000 to 1 lakh car is what is sold annually last year, the pure electric cars. Anyway, I am not considering hybrid vehicles, because hybrid vehicles does not have the future in India, because there is no subsidy for hybrid vehicles. Only the subsidy what we have is only for pure electric, battery electric vehicles. Maybe hydrogen also will have that, but the currently battery electric vehicles have been considered in the policy. Let us take this example. So based on our GDP growth, India is expected to have 7 to 9 million vehicles annually produced for actually Indian market. So 30%, let us take 30% of it, it is going to be 2.1 to 3 million electric vehicles on road in India. Because the expected GDP growth is, typically we might reach 7 trillion in 2030, is because we are going to achieve 5 trillion by 2025, which is going to happen because currently we are at 3.8 trillion. So when you have 2.1 to 3 million vehicles, electric vehicle, imagine how actually our infrastructure is going to be and how all actually they can support us. We'll see that in the next slides. So what are the electric vehicles actually I am trying to refer here which can sustain in India? So I have taken actually two technology. One is battery electric vehicles, another is the fuel cell electric vehicle. In battery electric vehicle, so though NMC started as actually the major, trump card holding the technology in batteries, but actually LFP is also taking up very quickly, is because it is all, the research and effort what people are putting in. LFP is mainly effort is put by Chinese, which today almost 70% of the batteries manufactured by Chinese, and they hold the complete scenario, this business scenario. And but however, both actually the technologies are existing. So basically, we store electrical energy in the chemical form here, and we utilize on our electric vehicle. So basically, the electric car, you will have the battery on the bottom frame to give you a good center of gravity and also stability for the car. And then you have all the power electronics either in the front wheel or in the back wheel, depending on the car manufacturer. Whereas in hydrogen vehicles, so hydrogen is your fuel which you store on your car, and you use the fuel cell to make the electricity. So where the fuel is hydrogen here, hydrogen goes on touching one of the electrode, and this side you take air, you see the oxygen, though ion exchange actually makes the electricity to flow there, and actually the reaction will result the heat out and also the water coming out of your exhaust. So and then you will have a DC-DC converter and then traction inverter, all that. So these are two technologies which actually are going to rule EV market in India. So maybe further details, I mean, why it actually makes sense, these investing in these two technologies or actually trusting these two technologies which actually change our scenario of the transportation. One is sustainable, is because it is always green, both are green, and both of them demand electricity. So and as we are investing in the renewables, which actually electricity comes from renewable, integration of renewable is very clearly mandated by the government, and definitely this will help us to run these both the technologies in India. And definitely the battery technology or fuel cell technology or motor efficiency, density, all what is required to achieve for a car to run sustainable car, it has been already done. And whatever the improvements, it's only pass on the benefit to these two technologies. And definitely when you see the costing, both technologies are actually running cost of both the technologies is not comparable. That means they are extremely cheap. So the fuel based vehicles are extremely expensive to run, because maybe the electric car would take maybe 1/7 of the cost what actually the fueled cars today consume. And definitely they are being, when we say that, they charge you very little to run, definitely they will be very high efficient. And definitely the other very important thing is all the car manufacturer or the energy infrastructure guy investing heavily to make them 24/7 available, especially from the charging infrastructure, support for these new technologies. So keeping all this in mind, they are giving a greater promise to change the scenario way we drive in the next years. But bottom line is, whatever I say, bottom line is how expensive are these cars, how cheap to run these cars. Actually these two things drive this whole technology or this business. Let us take example how cost effective are battery electric vehicles. Typically if you do a household charging, you will end up actually running these cars at most expensive would be 1.3 rupees per kilometer. In case if you produce electricity by yourself with your solar, it is going to be maybe less than 0.5, half a rupee per kilometer. So I am taken a commercial one, which I mean your household cost, which is Karnataka cost you 7 rupees per kilowatt hour. So and then typically inefficient electric car consumes around 18.5 kilowatt hour per 100 kilometer. It could be much more efficient, because if you drive in city, the car should be more efficient. They might even give you 150 kilometers. So in that scenario, it is only costing you 1 rupee 30 paisa per kilometer. If you see a fuel vehicle, a petrol car, it nothing less than 8 rupees or 9 rupees per kilometer what it costs you. And definitely everything depends on, this is the fuel. Here the fuel is this electricity. If this is cheaper, it is cheaper. And if I want to charge this in Germany today, it's very expensive, unless until government pass on the benefit to me, because in Germany it costs you today 50 cent euro per kilowatt hour, very very expensive. Unless until you get the subsidy on charging electric vehicle, it is not going to be viable. But in India, solar if you make, it is going to be 2 rupee 20 paisa per kilowatt hour. If I take from electricity from the BESCOM, it is going to be 7 rupees. Commercial, if you go outside charging stations, they charge you around 18 rupees per kilowatt hour on highways or in your shopping malls if you want to charge. Then it is going to be 3 rupee 30 paisa per kilometer. So what this scenario tells me is that this is a very strong contender, which, because running cost is very, very important in India for anybody, whether not only in India, whether it is America, whether it is Europe. Running cost is very, very important because we like to run more. So when I'm running, actually, if it is cost is very cost effective, makes sense, sustainable. And what actually the typical charging times, what it takes, if you go for AC chargers in the night, overnight charging is required. This is where I refer 7 rupee per kilowatt hour. If you want to have the fast charger, which costs you around 18 rupees per kilowatt hour, it could be anywhere between 50 minutes to 1.5 hours. This limitation is not coming by the charging infrastructure. There is a little charging infrastructure to play a role in that, the charging time as well, but it is more from the battery side. If battery can accept, they can be much faster too. The highest efficiency, because we are able to achieve all this is because overall efficiency from renewable production to battery storing and using for the propelling my vehicle, it is achieves much higher than actually 85%, typically 85%. So definitely this is because it is a very high charging time overnight, it is actually for the day usage, for the personal. Whereas coming to the fuel cell electric vehicles, typically the hydrogen production cost is, let us take, lowest would be, if I do hydrogen myself, which is hypothetical, if I do it in my home, it would be 7 rupee per kilowatt hour energy what I use. If I do commercially, it is 18 rupees. I have taken the same here, but the comparison can be drawn out very clearly. Typically, it takes to produce 1 kg of hydrogen, you need 49 kilowatt hour of electricity. That costs you around 343 rupees to 884 rupee per kg is the hydrogen production cost. And if you calculate all that, the 1 kg of hydrogen is equal to 33 kilowatt hour of electrical energy, and then if you run the because all our propulsion is electrical here, right? If you calculate based on that efficiency and everything, it typically comes around 2 rupee 85 paisa. More than double of what you see here, 1.3 rupees. But still, this is very, very viable compared to today's fueled vehicles. Fossil fuel vehicles are actually very, very expensive to run compared to this. But however, if you see the scenario, what they say, 2030, the green hydrogen produced by alkaline or PEM, which is going to reach $1.1 to $2 per kg of hydrogen. This is all actually comes if I have an infrastructure to produce hydrogen. The way Adani, Ambanis are talking about in India, the kind of hydrogen they want to produce it, if they produce, where they have to use it? See, our India's need for fertilizer production or chemical production is today need is 6 million metric ton. So the kind of what actually they are talking is, they were planning something like 20 to 25 million metric ton of hydrogen production every year just for the transportation. Why transportation it makes sense is, you need hardly less than 5 minutes to fill up your hydrogen if you have a station. This is where is the trump card it holds compared to electric vehicles. So and definitely the efficiency wise, this is not the best efficiency, is because I need to do the two conversion. I take electricity from the renewables, I make hydrogen. So efficiency what I can achieve is only 70 to 72%. And then again, once I make hydrogen to make it my propulsion, so I take another 72% is only my efficiency. So 70 to 72, approximately it is 50% only. But however, though it is 50%, being my electricity cost, if it is smaller, it becomes very viable. Definitely when you compare with this will be more efficient. But whether they will compete each other, they are not going to compete each other. It's because they hold their own trump cards in their segments. For example, see for buses, trucks, if you want to make with the battery storage, electric vehicles, it is very difficult. It's because, let us say bus carries 300 kilowatt hour of energy storage to run maybe 300 kilometers. So if you want to charge that guy has to stay maybe for 2 hours in a station. So 2 hours vehicle stopping is a big loss for the investor. These vehicles have to be continuously running. So they are very highly suitable for continuous duty applications. Truck guy don't have time to wait for 2 hours. So if there are no, if he is overnight he wants to always take rest, it is always a possibility. But normally trucks will have 2 drivers, they drive, one guy drive in the day, another guy drive in the night. They don't want to stop their vehicle because capital investment is very high. both technologies are going to be there in existence, complementing each other. That's more important, and then we have to invest, or we have to focus technology on the both the sides. The beauty is both of them uses similar technology. There is not much of a difference. So typical in electric, the power electronics application on a electric vehicle, see, it uses lots of power electronics products. Most important ones are the onboard charger. Where is onboard charger? Okay. Onboard charger, which actually takes AC from your home or from commercial and actually charges your battery, which is there on the backside. And another important is the traction inverter, which actually drives your vehicle. So, and then definitely the motor. So Delta has all the product segments. What is being shown here is has all the products for our customers. So there are some specific things. For example, some customer needs onboard charger, traction inverter, and DC-DC. This DC-DC is basically you have a high voltage battery and low voltage battery. High voltage could be 800 volt battery, which stores energy for propulsion, and then you have a small 12 volts battery, which is for your electronics. People thought, everything will be driven by one battery, but the automotive industry is not so easy to change there, because they don't want to touch their infotainment, control, and safety electronics. So they wanted to keep on 12 volts. So hence, for an energy exchange, you need a DC-DC which actually does that job. So some customers demand everything is together, because they say that it is all power electronics, you only supply, you pack everything and supply me as a one piece. So we have a different variants, but actually very important is onboard charger, then the DC-DC, and then the traction inverter and traction motor. These are the four key parts of power electronics which goes in automotive. Definitely, whether it is the battery electric vehicle or green hydrogen, the fuel cell electric vehicle, they need actually the charging. So here is an electric charging infrastructure. Here is the charging hydrogen into your tanks. Whereas actually the both sources, the energy source comes from the renewable. India is not going to supply hydrogen to their vehicles, not by the fossil fuel, electricity made by fossil fuel. It is going to be the green electricity only. So major important is energy source, and then number two is the charging and refueling. If these two are there, running these two technologies is very, very easy. If we don't have these, it is not going to work. So let us look the scenario of actually the renewables in India. So government is pushing now. Currently we are at 393 at 21. Could be now, I think we have gone somewhere around 410 gigawatt. Not really a fast growth. But however, by 2030 it is going to be 817 gigawatt of electricity. This is all for what? This is all majorly for our own current industrial and domestic need. This is not actually considering anything for the green hydrogen, not considering anything for the electric vehicle charging energy. In addition to this, there is an additional cabinet approval for another 125 gigawatt just to produce hydrogen, not even for the electric vehicles. Just still they are focusing mainly for the ammonia production and then the refineries. Another 125 gigawatt of solar. Then what about EVs? We will not run EVs by the electricity which is actually a polluting electricity. It has to be from the green. Imagine EVs plant on green energy demand additional of another 10 gigawatt annually from 2030. So why, from where it comes? 2 to 3 million electric cars and then another 10 million of two-wheelers. See, I have not even touched the two-wheeler, because two-wheeler is going to be the biggest market in India compared to even the cars. Cars are going to be somewhere in the 2 to 3 million. The bikes should be somewhere in 10 million. Imagine kind of battery they will carry. 3 million cars every year. So when you sum it up, this is what is the total solar investment, solar or wind, whatever you can consider, because India focusing maybe 20% wind and 80% going to be the solar. By 2030, we will have 80 gigawatt per year. It is not some, it is 80 gigawatt per year of solar investment in India. So which is coming from some from the for the EVs, and some from the hydrogen production, some from our own domestic need. So when you have this kind of an solar, renewable penetration, we have to be very careful with our power system. If we miss anything in this sequence, right, we are not going to achieve what is required. 3 million cars by 2030, it is possible only if we meet 1, 2, 3 what I have shown in my slide. Number one, now if I have this kind of penetration of renewables, how grid is going to be? See, let us take an example of, the deficit in supply and demand. So the supply I have taken, this is actually a plant which is, a very sophisticated plant, refined plant, or what we call very disciplined plant like thermal plant or pumped storage plants. So where, the energy it can smoothly supply. But actually demand could be fluctuating, because demand is always fluctuating. Whenever you have this deficit, you have the frequency starts fluctuating. So this is your 50 hertz, and it fluctuates on the plus and minus thresholds. So whenever you have the supply is higher than the demand, so you hit the upper limit. So when you have actually here you will hit the bottom limit. So both are not good scenario for actually stability of the grid. So this mainly happens, the shown criteria, shown situation is when renewable penetration is not there. And in India, if the renewable penetration, the kind I am talking, which is going to be more than 50% renewable penetration in India, these kind of plants when they run, let's say this is one of our wind plant in a day's record. So this plant is a 500 megawatt plant. So at the receiving station when we see, these are the fluctuating powers it produces over a day. See, from almost 500 megawatt, it actually falls down to less than 50 megawatt of power within no time. Grid don't like such actually behavior for its stability point of view. Similarly, the solar is also no good. Solar also can create this kind of situations anytime. So basically, the grid does not like actually the rate of change of power with the rate of change of power. Another challenge what we have is, so you have these renewable plants, and then which normally we have 690 volt, we are going all the way up to 1000 volts now, these generating stations. We step it up to 33 kV till we send this to the receiving station, or from here it is connected to the grid. So you have a distance close to around 50 to 200 kilometer, and as our profile is not fixed, this line actually behaves very badly for the grid. So it's because this can become capacitive and this can become inductive too. So normally under no load conditions, this is completely capacitive. So this 220 or 400 kilovolt line or 400 kilovolt voltage on this side, it can fluctuate as high as 480 kilovolt. At that point of time, they have to disconnect these plants. Otherwise, this is a nuisance. Typically here we have to install our actually power quality equipments just to make sure voltage is regulated. What is the thumb rule? If you have 100 megawatt of plant here, you should have 20% minimum. This is what is China follows, but India they are telling now it has to be 30%. So this actually responsibility is only support the voltage fluctuations. Don't bother these guys to stop their generations. Let them, these guys generate. We provide the sophisticated grid. This is on the power quality side supporting. And to support the same thing, I have taken some data from German grid. If you don't have the wind farms which are connected to certain grid, you have actually a voltage profile which actually, voltage is expected to vary, but it actually varies with a low frequency. But moment you have the wind turbines connected, you have the higher frequencies. So this frequency causes problem because this AC line, it is always a resonance, it perturbs the resonance, and then some location the voltage shoots up, and then all circuit breakers tum 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 gaya. Because the circuit breakers of a 400 kV line, if it crosses 480 and if you don't protect it, circuit breaker gone. To fix that circuit breaker, you take at least 6 hours. So another approach in India, what it works best is, let us say you have, let's say renewable, whether it is wind or solar, you have always a converter before you connect it to the grid, 33 kilovolt. So normally, whether it is a solar or wind, it is fluctuating as I mentioned. This is taken as a, let us take 1 megawatt solar plant, it's always continuously fluctuating. This fluctuates almost full power in 4 seconds. This is a typical rate of change of power. 1 megawatt can change within 4 seconds, which is not good for the grid. So in that scenario, but normally my grid, India says that it is a 16 point, the first order time constant of 4 seconds is what is demanding now government, but implementation is still yet to happen because there is a lot of investment has to be considered in the back end. Typically this is the power what we expect to pump in into the grid, which is actually supports the stability of the power system stability. To do this, you need to have in between somebody who is a buffer here. So buffer is basically you have a power converter and then a back-end storage here with the battery. But the storages are not small. Typically, if you want to achieve this, 1 megawatt plant would need minimum 100 to 150 kilowatt hour. If a plant of 100 gigawatt, imagine 15 gigawatt hour of storage is required. But it is required. In India, it's still better. Japan is demanding 40%. That means if you have 100 gigawatt plant, 40 gigawatt hour of storage is what is they are demanding. But anyway, it is good business for Power Electronics and my company. Then definitely you have PCS and BESS, so you need to have site controller, all these things and monitoring, blah, blah, all the software related. But this being, because moment you have PCS and BESS, this can become a microgrid here. That's a greater advantage. So you can provide lot of other features here. You can even disconnect the grid and run on your own. These are the additional benefits what it passes on. But these scenarios will work only if there is a proper norm and support from the government. That's how even solar is able to happen in India today is only because of that. So let us come now, see what I was trying to show is here, increased demand is happening because of India's industry need, green hydrogen increase, railway transportation energy requirement is also enormously increasing is because, for example, our regular Shatabdi train or Rajdhani train consumes hardly 6,000 horsepower or 9,000 horsepower is its peak power. Not 9,000, 6,000 horsepower only. Now the Vande Bharat takes 12 megawatt of power because we need speed. To accelerate you need that power, not for cruising. Acceleration demands almost double power. Let us assume on the same lines if I run the two Vande Bharat, my traction substation shuts down because my traction substation is only 21 MVA. And when two Vande Bharat runs between let's say Chennai to Bangalore, it is expected to shut down. So demand from them also increases. See, the government will push even railways that you make sure that you don't demand too much from me because they cannot change infrastructure so easily unless until they make a dedicated line. Okay, coming back here. So my increased demand is because of this. So what is that actually increasing? So my penetration 23%, it may go to 60%. Expected to reach only with industry is 53%. So I am considering green hydrogen and the EV demand. So this will 60%. Imagine 60% renewable pumping into our grids. It is very, very scary to even imagine that. So unless until we have the back-end support from the buffers, whether it is pump storage or battery storage or some sort of buffer in the grid, it is impossible. So definitely. So what actually this pushes us in power electronics is we need to have a very good sophisticated support to support on the transmission lines. Then we have on the generation side how we can actually improve. We become more sophisticated with our actually renewables. So that is with the battery energy systems, microgrids, battery energy system, ancillary service, and then the smart EV charging. Because EV is also going to be the important consumer in this segment. So we have to be very careful. The kind of EV charging stations we make have to support even the grids. Why I am telling this is 3 million of EV cars means what is the capacity they have? 75 gigawatt hour of battery they have. That means this size of battery is always available when they are connected onto grid. This is annual investment. Let's say 10 year I invest 3 million only. It is going to be 750 gigawatt hour of battery I have at my disposal. When they are connected on the grid, if they have this V2X feature on it, and if my load flow system, load dispatch center can communicate with them, they can always tell, instead of charging, you discharge or charge, do something which actually supports to the grid. This is all looks hypothetical, but it is like our digital economy, what has happened in last 10 years in India. If we have connections implemented, digital connections implemented, V2X supporting with this kind of energy storage for our grid, it is going to be practical. It is going to be implementable. So definitely, see, many of companies are implementing. See, for example, in our company, we have 20 car charging stations and 150 bike charging stations. They all run on renewables. They don't consume anything from the outside. So for that, what you need is you need to have your own microgrid inside, which ensures the smoothing of your solar, what is being installed on the rooftop, and then you become more sophisticated like any plant which behaves. So this will definitely, it has an investment, but actually this supports the grid. Similarly, in your household, if you have this V2X features, you can always support the grid, though you have a small battery. That help actually passes on. I mean, when the number of people who supports the grid
it becomes very high, even a small support will become actually very big at the end. It is like a drop makes river and then to sea. Another possibility is, let us say you have a huge investment, like you have multiple big DC chargers and then few AC chargers too, which actually, let's say, amounting more than 250 kilowatt plus of a charging station, which I have taken. You have 5 to 10 charging stations in your premises. Typical charger rating something around 16 kilowatt, 100 kilowatt. 16 kilowatt is gone. This is only a Bharat charger. Now it is no more. Let us say if you have 100 kilowatt kind of chargers, you would need a connection from the electricity would be 250 kVA. So moment you go more than 100 kVA, so you need to have your own transformer. You have to have a HT connection. So you should have either 11 kV or 33 kV connection. So this will actually demand high energy tariffs, and high minimum charges is because you are connected with the connected load is very high. So definitely that also adds to your maximum demand charges what it comes from. And then definitely the location challenges also. Let's say if I want to install somewhere in Yeshwantpur, it is impossible. It's because Yeshwantpur is so crowded, he cannot put a line for you and dedicate it. Though you have a space to install charging station, the electricity board will not be able to serve. Even if he supplies, let's say with the underground cable, it cost becomes very, very high. So in such scenarios, because to install, let's say 10 charging stations, you can easily have actually a space, roof space of 2000 meter square. It's because if it is a battery electric vehicle, the car owner demands, there is a shade, because he never wants to charge his car in sunlight. No? It is not good for the battery too. So you will have definitely you will have a shade, which is of 2000 square meter. Is very easy to get it if you have 10 charging ports. So when you take such a scenario, solar could be 150 kilowatt peak, which you can install on your roof where actually cars are used to charge. Then if you can make actually AC grid here, even if grid is not there, you can actually do your business here. So this gives all those features. So what we call actually microgrid suits, it actually helps you to reduce your energy tariffs, minimum charges, and then maximum demand. So what I am trying to say here is we have to think something innovative, especially in the charging stations as well, to make actually support the grids. And then it is not only supporting grid, actually it becomes sustainable, otherwise it is not sustainable. So other option is DC coupled, where you have the energy could be coming from your grid or from PV system. So instead of actually converting it to the AC, so you can use a DC-DC MPPT and then you charge in the battery, and also actually there is a PCS which makes the microgrid. So similar to AC coupled, you can also think of DC coupled. Normally AC coupled works very well if your sizes are bigger. So DC coupled is good when it actually the power is smaller. Commercially is because moment you go for a bigger power, solar inverters are cheaper. So AC coupling becomes the most efficient one would be definitely the DC coupled one. Okay. So the energy storage functions which we have to focus when we have this kind of renewable penetration is the smoothing and firming. This I have already shown. So typically the solar actually produces this fluctuating power. This is what is typically the expected from the grid. To do this you need to have a buffer, which is a battery storage. What we call this as either smoothing, because it is smoothing, or firming. Firming means you firm the energy what you produce. Basically that is the buffer job only. Then comes is the frequency regulation. This is what I refer is the primary frequency support. So normally in India it is so far not possible to implement, is because this needs a very strong guideline from the energy producer. Because though I invest to support this, and how do they pay me? So there is no rule at this moment. But in Europe it is very common. Germany has implemented the first guys. So what is actually this frequency support, primary frequency control? Let us take in Europe, in France, there is one power plant goes outage. So your frequency, though it was here, moment it actually the shutdown, the frequency falls down. So moment frequency falls down, the one who kicks up first within 0.5 minutes is actually one which is connected to power electronics. Nothing else can turn on in such a short time. So power electronics connected everywhere, distributed all over Europe, they kicks up. So let's say battery energy storage is distributed all over Europe, they kicks in. So definitely frequency either stays there or actually try to improve. but they don't have enough energy, because battery cannot give you like hours of energy, is because then investment becomes very, very high. Typically is expected is 15 minutes. Within 15 minutes, the secondary generating plants will turn on, like it could be diesel generator, gas turbines, all these actually can turn on in 15 minutes. And then there is a tertiary, which are really big. So these are very small energy, 15 minute support, then comes is 30 minute support, then comes is the long term. So there could be one of the big, the plant, generating plants will turn on and support the grid. So this is very well works. I mean, without this, if you don't do anything in this 15 minutes, you will collapse, grid will collapse. Then comes is the peak shaving and shifting. This is typically in an industry, what happens, whenever you are turning on your furnaces only for 10 minutes, 15 minutes in the peak of the day when other loads are also there, you will start actually demanding the, for example here, you will be start demanding this peak powers. Just because of this peak power, you have to pay extra money. So this is what we call MD. When you buy it from the electricity board, so if you draw any peak power for 15 minutes of average, so that is considered as the maximum demand from your company. Even though if you are at 100 kilowatt is what is the 100 kVA is connected load, 120 you draw only for 15 minutes, so then you are charged whole month for that MD for the 120. So in order to avoid this, normally we call it as peak shaving. So shifting is from the renewables. So let's say this is a renewable production, but the load is something like this. So you know that this energy is not used in the day, you dump this in the battery, and later in the evening you use it when actually the solar is not working. This is very straightforward. The other feature what we have to provide with our new infrastructure is on the power quality, which supports for reactive power, harmonic, unbalanced and transients. Maybe not, because any power electronics which is connected in shunt, it can do it easily. Coming to now, chargers and their details, how these the current charging infrastructure, these chargers are utilized. We have actually 3 sets. Highest number sold chargers are the cord chargers. Every car actually gives you at a free of cost. This could be 5 or 15 ampere. In India, it is more than 15 ampere is not allowed because you don't have the socket. Then you have these two are commercial ones, 3.3 to 22 kilowatt AC, and then you have 30 kilowatt all the way up to 350 kilowatt commercially, which is available today in India. All are actually for the commercial. Definitely this is the most expensive one because it's DC and is also not good for your battery, because the battery life comes down if you do more DC charging. This is more for the highway usage charging. And AC chargers, these are typically for the commercials where in the malls and even on the highways they are installed. But the beauty is, this is the maximum number. This, neither of these has intelligence, no intelligence they have, no power electronics also. What they have is, this guy has only the protection. If there is current demand is more than what is being asked, it shuts down and it sends an alarm. Whereas this has a billing. The same thing with a higher power, up to 22 kVA it can give with the billing, because this is for the commercial. So you have to swipe, you have to pay and you have to use. This also has a billing, this has a power electronics. So what actually typical DC chargers today from the power electronics point of view we have? We have 3 approaches. We have rectifier based EVCS. The isolation is done at the rectifier stage. So once you make with the PFC, you have a DC bus, then you have DC-DC with the isolation. And you have the central EVCS where actually the isolation is done at the central station, central portion, and actually rest all is actually non-isolated. Because the conversion is very high here, conversion efficiency is very high, conversion efficiency is poor here. And the most efficient one would be SST based technology, so solid state transformer based philosophy, though this side is not AC. So you take 3-phase grid and make the DC. So isolation is done with a single transformer here. This is a coupled transformer for how many hour outputs you want. If you want 4 outputs, you will use 4 isolation with the 4 windings or 5 windings on one transformer. Definitely this is the most popular right now because it is evolved much faster and you have the programmability. If somebody wants 100 kilowatt, you add actually 25 kilowatt rectifiers, 4 of them. If you want 125, you add 1 more rectifier. The programmability is very easy and then you can actually deploy rectifiers systems very fast. But our efficiency point of view, you cannot achieve anything more than 94-95%, because this transformer is mandatory, because the connections, if you see let's say 4 bus charging, that means you need to have something like 500 kVA of connection. That means this transformer is mandatory from the grid point of view. If power is smaller, then definitely it makes sense. So such big charging infrastructures, this would be the most optimal one right now, because this technology is still to mature. This technology is not mature, especially in high power. Today this is the trend, though actually people, one who demands more than 350 to in this class, still people go with the 250 kilowatt, because this is commercially very popular at this moment. So viability is the key thing. So but however, this is the future where, you know, this has, because there is a clear disconnection from the AC grid to your outputs, is because both sides it is active. So any fluctuations on this side does not influence. If you have a storage on this side, even actually you can run on the microgrid. So that's the beauty. But however, we don't have the today permission to connect a solid state transformer to grid, is because of the protection point of view. Still the norm has to come from our CRRCs, regulatory authorities. Coming to the onboard chargers, which is a very important part of the electric vehicle. This is onboard. So far I discussed was about generation and then the charging infrastructure. Now comes is power electronics on the cars. So OBCM is the one, as I mentioned, the three power electronics are very, very important on cars. One is onboard charger, which charges from AC to your high voltage DC into your battery. Number two is a traction inverter and motor. Three is the DC-DC, which charges between the high voltage battery to the low voltage battery. So onboard charger, which fits most probably in the front portion, which actually gets the AC input, and the DC is charging to your battery, what you have here. If you see, we commercialized these products since 2017. So with initially with the Daimler with 3.3 to 3.6 kilowatt onboard chargers. So now we are commercialized 22. From 3.3 it has gone to 22 kilowatt. I think beyond going 22 kilowatt, it is practically not viable, is because the kind of AC ports you need to provide the power is very, very difficult. It's from the infrastructure point of view, not from the power electronics point of view. So today, in 17, when we started, the efficiency was somewhere around 93%. So today is expected to go, our all new products will have 97% efficiency. This we are able to do with the wide band gap devices. And we also learned how to pack, how to improve density without losing on the efficiency. This is all experience. Power electronics or engineering is, without the experience, will not be able to achieve the kind of the demand what market asks for. And coming to the topology, see, you have onboard chargers. You have actually the typically the unidirectional used to be the trend. Now actually everybody demands a bidirectional onboard charger, which is the current trend. So you have two approaches. Let's say if I have to do 11 kilowatt, so or 10 kilowatt, so you can go for 3.3 kilowatt modules in parallel. Why I tell this is, we had actually bread and butter 3.3 we had made. So we propose to have 3.3 in parallel, but this actually does not give you the best from the price point of view, all that. So we have to have something which gives you density is also higher, and then gives a better efficiency. So you have other option is, you make one PFC of 10 kilowatt and then 10 kilowatt of bidirectional DC-DC on the charging side. So typically it is because bidirectional is required, though we have many other topologies to do that, it is all actually our experience. You see, for example, so in India we use these topologies to meet our customer needs. When I go to the China, they go for series resonant converter, especially for the isolation. It is all our experience. It is not that, you know, the one technology is always actually what drives the best result. It is not true. It is about my experience, what topology I know better, I know how to do it more efficiently, is what actually matters there. And typically the efficiency of on the secondary side, what we have achieved in the latest one is around 98.3%. This is a commercial product what I am talking. Together if you see, we are achieving somewhere close to around 96.5 to 97%. And coming to the traction inverters, back in late 2017-18, when we launched our first product, was in 100 to 150 kilowatt range. These were all actually, when we say 100 to 150 means, some customer demands 125, some demands 127, 140. So I cannot make the platform so different. Only what actually changes is actually the body, because every customer has his own specific needs. But inside, if you see power electronics, more or less we keep same, because we will not be able to have that kind of bandwidth or money to invest, make every new model for every new customer. That's why we will have a different platform. This greater than 200 kilowatt attack is around 350 kilowatt platform. So this can go up to 350 kilowatt. So 150 kilowatt, which achieved somewhere of this kind of efficiency. So we achieve now target is 99% what we have to go. Definitely this is possible with the we are able to achieve this density and the efficiency is because it is supported by the new devices what available. And also because of high switching frequency, I am able to achieve this density because my capacitor also big. What is there inside is not really anything great. You have the capacitor and then you have the devices and then the cooling. So all comes together. For example, this package is 350 kilowatt on which actually there is one additional PCB which sits. It is for the communication backend. Today it is more about engineering than actually, especially delivering this product is more about engineering than actually the technology. Definitely this has helped us, but rest all if you see it is very conventional because inverter we know doing more than 50 years. Here also if you see topology is standard, either 2 level, T-type is very few where actually customer wants to give that extra money for that additional efficiency and performance, but otherwise is 2 level IGBT only. Very important is reliable communication software. What I have to give on this inverter is most important. The motor control is option. Customer many a time says, I have my own control. I will control my motor myself. You don't do anything. Some customers who are actually comes from very mechanical background, they say that, okay, please do the control also. It is a plug and play software piece what actually we keep prepared ready. And whenever my customer demands, we provide that. Because this is very mature technology, so we don't do anything great in that. Yeah, with this slide, I finish my presentation. Thanks for your patience, and then I look forward for your questions.
Customer, I would prefer battery under my sheets rather than hydrogen cylinders. So how safe they are? Hydrogen fuel cell.
See, I mean, it is very difficult to digest. When you talk to the Toyota guys, they themselves don't know why people believe that the hydrogen cylinder is unsafe to his customers. It is all our mindset. See, you have LPG your home, you feel unsafe.
No. But we because we have hydrogen bomb, we don't have battery bomb.
No, it is not bomb, huh? It is hydrogen. There is a difference.
Yeah, that's in our mind.
Yeah.
So means they are.
See, for example, in hydrogen cars, the cylinder is a very key thing. Even in LPG, cylinder is very key thing. Wherever you are pressurized, you see, hydrogen is the lightest element on the earth, right? We all know. So it can, the sweep away even in actually when you pack in a steel tank. It has to be a special tank, and that too because the density is so low, you have to put them with very high pressure. They go with lots of high pressure because you want to pack 1 kg. Because you see, I have shown that that Mirai car. See, it carries only 5 kg fuel. Huh? There's only 5 kg, which runs you 600 kilometer. 5 kg. That actual mass, if you see, it is only 5 kgs. But you have to pack cylinder. He needs 3 cylinders to pack that. You can see this. So, but it is, if it is not engineered well, both are risky. Even equally, IC engine is also risky. Huh? So, because recently you might have seen in one unfortunate accident happened in Maharashtra, right? The bus. So, why did it got fired? Because of the tank. I mean, there was a friction between the tank and diesel came out, and then with the barricade, fire. Any fuel we carry, if it is not engineered or maintained properly, so it is risky only.
Thanks for the presentation. A quick question about the vehicle to grid and vehicle to home. So do you see the economics there? Because nowadays the battery warranty is based on basically cycle discharge, discharging cycle. So obviously when you do this vehicle to grid or vehicle to home, we are increasing this charging discharge.
If it is imposed by the government and no questions asked. If it is not imposed, then we will all ask these questions. They have to provide the infrastructure and then they have to impose. You see, it is all for, at the end, what? For our own country, right? Our own grid. So if they say you have to support when it is connected, it is not under your control. If that particular requirement, algorithm is been embedded, it will be embedded for every car. Even you don't know when it is connected. Only you can disconnect and say that, okay, I was not connected to the grid, and then I am not supporting this. If you are connected, then it is actually the control will take over.
Not discourage the customers to
No,
take up
it will
electric
not.
cars.
It will
Because
not. See what is happening currently, why we are bothered. See, if I do too many times of charging and discharging, so my battery life will go down. That is true today, but actually over the period of 5 years you don't know.
So with respect to one of the slides where you explained the economics of setting up a charging station and rather setting up a micro grid where 2,000 meter square kind of a plot is required, probably to set up a solar power system, right? Infrastructure. So I mean, isn't that too big and then impedance?
What happens,
to
sir? Let's say I have said you 10 charging station, right? To park 10 cars.
But
kind-
the current requirement with respect to the fueling stations, right? It is like 800 meters
Definitely.
square.
I am not at all comparing with the fueling station. If let's say I want to invest for a 10 car charging station. See, even today, why people are setting up the charging stations? It is commercially viable to them. Because they are selling you electricity at 18 rupees per kilowatt hour when they charge it. On highways, the real estate is very cheap. In cities, it is not workable. It's because that kind of power also getting is very, very challenging. So there only one charging station would work, one car only, and then no microgrid is possible there.
Yeah.
If we have 10 charging stations where you have the space, and you also do see the customer who comes there, he will wait there for 1 hour to charge his car, right? So you also have to provide a coffee shop. There's a further economics. So hence he will have that kind of floor, and then he will be able to invest solar for that. It's only option to him. By that he will be able to maybe, see, we worked out typically in our office also, ROI with the most expensive solar panels and the standard cost of the battery and PCS, ROI is 5.5 years.
But then is that 2,000 meter square minimum
No,
viable?
it is only one thumb rule. I'm just giving there that this is the kind of space you would need, and then you utilize the space, I'm telling.